Okay, it's not like that. Let me share my screen. Oh, not from here. I have to share my screen from iPad. Can you see my whiteboard screen?
Yes.
Okay, thank you. Thanks for confirming. Okay. So before I start, let's recap something that we actually learned from our last class. Last class, actually, what we learned in our last class. Main thing was if we go for the summary of our last class, address space. And so there are two types of address spaces. One is the physical address spaces. One is, you can say, one is physical. Another is logical address space. Logical address space. These two concepts is very important. This keep in mind. Physical address actually is address collection of address from our memory or RAM. RAM is random access memory, or you can say simply you can say RAM or memory. And logical address, the address collection of address from our process. What is process? Process is nothing but a program, execution phase of program or execution phase of a software. You can say software is nothing but itself. It is a program, and also program is also kind of executing phase of process is kind of a executive phase of a program. So it is we can use it interchangeably. These are almost the similar things. So logical address space address a collection of address from our process. This is a logical address space. And next we saw that there are some memory allocation methods. One is contiguous allocation, another is non-contiguous allocation. We didn't learn anything from our non-contiguous allocation, but we learned two things from our contiguous allocation. Contiguous allocation. What is two things? One is fixed partitioning. One is fixed partitioning. Another is called variable partitioning. Variable partitioning. Fixed partitioning is also known as the static partitioning, and variable partitioning is also known as the dynamic partitioning. And from our study last year, we also saw that there are two major problems for both of these partitioning. One major problem for both of these partitioning. For fixed partitioning, you just fixed before when you turn on your PC, your memory is partitioned by several fixed spaces. So let's say it is partitioned in 3 spaces. So you can actually accommodate at best 3 processes in for this fixed partitioning allocations. But if you insert a process, let's say this is 10 MB space. If you insert a process like 8 MB, but when a 2 MB process comes, you cannot fit it in here because one process is already actually occupied by this space. So you can so this 2 space is going to be wasted. So this is called the internal fragmentation problem. Similarly, when you use the variable partitioning, for example, here is one process and here is one, let's say this is a whole or backend space. This is, let's say this is 5 MB. Also here is also 5 MB. And this is also some process is there. And also here is also backend space. Here is also process. This, let's say 5 MB as well, 5 MB as well. Okay. If new process comes at 10 MB, even though there is 5 plus 5, 10 is available, but you cannot accommodate this 10 MB process. Why? Because this is contiguous memory allocation. What is contiguous memory allocation? You have to actually accommodate a process inside the RAM in a contiguous addresses, physical addresses. Let's say this is 0, this is 1, this is 2, this is 3, and 4, and so on. So you cannot allocate 10 MB from this 10 MB, 5 MB in here, and also 5 MB in here, because this is not contiguous physical addressing. This is 1, this is 3. 2 is another. 2 is actually address accommodated by the another process. So you cannot actually divide it in say you cannot actually put one portion of in a location, another portion is kind of different location. You cannot do this because you just that time you just violate the condition for contiguous addresses or contiguous addressing. So you cannot do this. So this kind of problem, this kind of hole is always is going to be wasted. So this is known as the external fragmentation. So internal fixed partitioning is suffered from the internal fragmentation. Also, variable partitioning is suffered by the external fragmentation. These are two major problems for both type of partitionings. And also, there are some others partitioning is able. Other problems is also there. You also read it. You can also read it from our slide. So any question? So I summarize everything in a slide called some additional underscore addition module to underscore additional. From there you can find all of these topics that that we learn in this session. So next, move to the our next item. So far you know that there is two types of partitioning, but you know that so when you actually at first class I mentioned that okay, let's see, this is make it this is your CPU, central processing unit. Also here is your RAM or memory, and here is your disks, SSD or HDD, your disks, permanent memory. This is RAM, random access memory. This is your hard drive, SSD. Also, it is SSD. So you know that when a CPU request for a process, it just first it starts in RAM. If it is not found, then it sends a request to the SSD or hard drive. What's then operating system actually for transfer the process from HDD to RAM? Actually, operating system actually involve this transformation. Also, here is also one transformation from RAM to CPU. There is also one transfer from RAM to CPU and CPU to RAM. Actually, back and forth. And then in here, what type? You know that operating system is also a complex. It is also a software, and it is a very complex software, and thousands of functions inside the operating system. F1, F2, and let's say and so on. Fn. Lots of functions. There is one function name is called the long-term scheduler, and another is called another function is here in operating system is short-term scheduler. Short-term scheduler. So to copy to actually move a process from SSD to RAM, actually short-term scheduler function actually work in here to move a process from your hard drive to RAM. here is short-term scheduler function actually involved to make this to actually involve this transformation. So let's see for that we actually learn that what kind of algorithm are actually used for short-term scheduler to transfer a process from SDT to RAM. And now let's consider that so far we study what we study. We study fixed partitioning. Let's say fixed partitioning. What kind of algorithms can a operating system use to transfer a process from your hard drive to RAM? You know that in your hard drive, every software program is available. When you double click, then it will create a copy of it. It is called the process, and this process actually operating system transfer to your SDD to RAM for executing by the CPU. Then from here, CPU actually can access your process, and it's executed by line, whatever you can. This thing you can consider in here. So right now so far what we saw that in contiguous partitioning. Let's see that what kind of algorithm can use for short-term scheduler. There are 4 different types of algorithms. Short-term your operating system can actually move a process from SDD to RAM in case of contiguous memory allocation. One is for fast feed. We'll learn elaborately later. Second is called the next feed. Is called next feed, and third one is best feed, and fourth one is called worst feed. These 4 kinds of algorithms used by the operating system to transfer a process from SDD to RAM in case of contiguous memory allocations. And let's say, and how it works. Let's say this is your RAM. This is your RAM, and here is already, let's say there is all, you know that OS is also a process. The OS is there, and then here is also process, and this is backend space, and here is also one process is there, and here is also one process. So you can imagine that this type of structure can happen any times. Let's say this type of structure for a current given time, it may happen. For example, this is let's say this is 10 MB process. Also, let's say this is for variable memory spacing, variable allocation, contiguous variable allocation. Contiguous variable allocation. This is 1 MB process. Here also 10 MB process was in here, but it's completed its execution, and now holds is created. And then also here this process is already in execution phase. Here, let's say this is 20 MB space. Space is available. Let's assume that here, let's say here 20 MB process was there, but it's completed to execute and creates the whole. And next here is already process is available for execution in execution phase. Let's say this is also 5 MB process. 5 MB process. So how fast it works? When a new process open or new process come from your when you try to open another new program or new software, then process is created. And then let's say this process size is 10 MB. 10 MB as well. 10 MB process. So how if your operating system follow the fast feed algorithm, how it searches? It's actually searching from the beginning of your RAM. Let's say this is user space. This is user space, and this part is the operating system space. From the beginning of the RAM memory, it starts searching where the hole is if a whole if a backend space actually is found by your operating systems that is fit for this 10 MB process, it just accommodate. It's never go beyond of it. Whenever it first time it find a hole that is enough to accommodate this process, then it just accommodate there. It just actually accommodate that places. This is how fast fit works. It start from this beginning, and then from in this example, it start from the beginning when 10 MB is found by your operating system. It just take this place and also fit this 10 MB process. If 10 MB, let's say this is not a backend space, this already process, already there is a process made can be there. So it starts searching from this beginning, search, and then here 10 MB is first time it's found the 20 MB. So 20 MB is enough to feed this 10 MB process. So it just take this spaces, take these spaces. It just it never search beyond of it. Another scenario can be, this is, let's say this is 10 MB backend space, 10 MB space here. Also this is backend. Let's say this is, let's say this is backend. Also here also 20 MB is also backend. Here is 8 MB backend, but your process size is 10 MB. So it is start from here 10 MB. It's found there is a hole for 8 MB. But your process size is 10 MB, so you cannot fit it. It should be process size, holes or backend, whole size should be is greater than or equal your process size. Then it can actually allocate the memory for this process. Otherwise, it cannot. 8 MB, but here is your process size is 10 MB. So it moves forward, and then here it will find the 20 MB free space. It just places this process in this hole. Okay. So from here, this is how a fast fit algorithm actually works. Do you have any question regarding the fast fit? Fast fit is nothing but it starts from searching from the beginning of your memory or RAM, and then whenever it find a suitable space, it just fit. The process will be fit for this whole or space. It never search beyond this. So there is one advantages for this fast fit. Could be one advantage. What is? It's for this best case. It may find the it may find a space within the fast group. For example, here once it takes here it's find there is no backend space. Here is 10 MB. It's just find this 10 MB space and just fit it to for this process. It doesn't require to search the entire address space in your memory. This is for the best case scenario. In case of worst case scenario, it needs to travels all of this address space in your actually memory to figure out that where is which space is suitable for this 10 MB process. This is some kind of advantages and disadvantages for best fit algorithms. So we can say this is the kind of advantages. It may find the backend space actually quickly in case if you use the fast fit algorithm for best case scenario. For worst case scenario, it will also search. It may needs to search the entire address space for your memory. So and next algorithm is next fit algorithm. Next fit algorithm. Okay. So now let's see what is next fit says. This is your. Let me change my color here. This is your RAM. Also here, of course, OS always be there. This is space for OS space, and this is for user space. And here is kind of, here is one process already there, and here could be, let's say here is also process. Here is backend, and here is also another process. It's like this. Here is also another process. It's like this. What's next is does it is similar as the best fit algorithm. At first, when a new process comes, it starts from the first address of your memory. If there is a suitable address actually find for this process or not, and search continue. Let's say this is 10 MB, 10 MB, or let's say this is 20 MB. It is fine to, it is good enough to feed this 10 MB process. It just take this space from here, 10 MB space from here, and feed it to the memory. And next, when a new process comes, another process you open, this is, let's say this is 5 MB process. You try to open another software or another program, it is 5 MB. So what's next it does, it is not like a fast speed. Fast speed always search. Whenever the new process comes, it's always search from the beginning of your actually memory. But next bit here, actually last time it's actually left it from here, from in this position. So when a new process comes, it start from this position. Not actually it doesn't start from the beginning of the time. When first process, it start from the beginning. When next when the consecutive process come, or next process come, it just start from this, when actually it's left from the last time. So it's last time it's found the space for 10 MB in here, so it start from the searches space for 5 MB process from that point. And here it's lucky, here is 10 MB is empty, so it just take the 5 MB from here, 5 MB from here, and 5 MB will be the vacation, the backend space. Backend space is kind of like this, backend space in here. So 5 MB is, it is kind of, advantage is kind of similar as the fast feed. In worst case, you may actually travel to entire address space in your memory. But for this best case, it may find the suitable spot actually quickly or swiftly. For example, here is 10 MB free consecutively, where actually left from for last time. So here it's find 10 MB just a one consecutive actually address, one is left from for the last time. So, and if it's not find in here, let's say it is not this is not a 5 MB, and it is also not a 5 MB, it's already backend, it's already backend. So what it does, it just search from the spot where actually left last time and search it, and then again it actually search from the beginning of your memory. Again it comes beginning of your memory. This is how actually next fits works. So in worst case, it also may need to actually travels entire address space in your memory, for in memory. And okay, so how actually computer how your algorithms knows this, where is whole, where is process? It's nothing but inside actually it's maintained as a linked list. You know about the linked list in a programming language. Here, let's say this is process, and this is the starting address. Here it's 0 to, let's say this is 0 to 100 for one process. This is 100 for one process, and then it lists there is another process. Let's say this is also process. It's let's 100 to 200 address. It is starting is 100 address, and next 200 address. The next is whole or backend space. It manages age, and then it is start from, let's say 200 to 300. Let's say 200 here, 200 here, and 300 here. And from this, it's just in first bit, it just travels this linked list. When it actually finds the age and find the address or space, total space for this hole. And if it is fit, then it just applies this process inside this hole or backend space. Okay. Any question regarding first fit and next fit? Both are actually same. Only difference is that next fit actually starts when a new process comes, that it instead it starts from the beginning. It starts searching from the searching from where actually left last time, process left last time, from here. Right. So this is two algorithms, and our next algorithm is best fit algorithm. So let's see what is best fit algorithms. Let me clear. Let me clear some part. Okay, now let me open one. Best new about this one. Okay. So now we learn the best fit algorithm for memory allocation. This algorithm, which function are essentially used. This algorithm usually use the function called the long-term scheduler. In operating system, there is one function is known as the long-term scheduler, and this long-term scheduler function usually use this type of algorithms to allocate the memory for upcoming process or current process. So what is best fit said? Best fit actually said that at first you have to traverse, you have to search, and the operating not actually at first your operating system search the entire address space from your memory, and it may find the more than one space where the process is fit to accommodate. Among these spaces, this algorithm select the smallest backend space. Here, one thing is that smallest backend space or smallest hole to accommodate it. For example, this is your memory, and here is already process. Here is also, let's say this is the backend or hole. We'll see here, and then here is also one process. Here is hole. Here is also hole. There is one process is there. So let's say this is 10 MB. This is also 10 MB. This is, let's say, 15 MB. This is also, let's say, 20 MB. This side is 20 MB. Yeah? This is 10 MB, 10 MB, 20 MB. Let's say one process comes in your RAM. Its size is, let's say 17 MB. Let's say 5 MB. 5 MB process. Currently, actually, operating system is working on this. Try to fit to the inside the RAM. So at first, it searches your entire address spaces in your for your RAM, and then it's figure out that, oh, there is 10 MB. They find the 10 MB, 10 MB, 15 MB, and 20 MB. All are actually suitable to fit this 5 MB processor, because process size is less than all of this whole size. So what best fit does among these holes, or among this backend space, it will take the smallest one to feed it to 5 MB. Here is 10 is the smallest. Here is 210. So it takes first one to backend this process. this process. So this is the best fit works. At first, it search entire address spaces, then figure out the number of holes that is actually uh, that is enough to fit your current processes, and from these processes it select the smallest one. This is how a best fit works. Do you get it? Okay, any question or comment? Yeah, it is. Okay. Okay, now see that what will be the problem for this best fit algorithm. First of all, in last two algorithm, you saw that it is first fit and next fit. It may find a solution. In best case, it may find the solution within a one go. For example, here is enough for 10 MB. Let's say this is the whole for 10 MB. So it just search from here and then here. Oh, it's good enough to insert the 5 MB process. So it just actually insert this process in this hole. It never travels this or entire address spaces. But in this case, best fit algorithms, you must require to travel entire address spaces to figure out the all holes that is good enough to fit this process, and from this process you have to figure out the smallest one. Okay. So another thing is that, let's say this process size is 8 instead of 5 MB. Let's say this is 8 or 9 MB. Let's say this is 8 MB process. So it is found the best fit algorithm is found the all four holes that is good enough to fit this at 8 MB current process. So it select the smallest one, 10 MB one, smallest one 10 MB. So it's inserted this process inside your RAM. So here is, let's say here is 8 MB for this process. So 2 MB is backend. 2 MB is backend in this hole. It takes 8 MB, but 2 MB is still unused. So what it makes here, it choose the smallest one, but in some cases it makes your small hole smaller, more smaller. So when a new process comes, you may think that process itself, it has actually space. It needs some space. Process. So you may not find the 2 MB process in your computer, or in your computer. Let's say, for example, it could be, but let's say, for example, you may not have this 2 MB process. So this type of small hole is always unused. So it may not actually your resource efficiently or optimally. This is the one problem of best fit algorithm. It chooses the smallest one, but it makes this smaller actually hole. Smallest hole is smaller. Smaller. This kind of problem actually affected by the best fit algorithm. And another, this is the one of the major problems. One thing is it takes travels the whole memory. Of course, it needs to traverse the whole address space in your memory, and also it may create the smaller hole. This is the problem for best fit algorithms. And another is the last one is algorithm is worst fit algorithm. Worst fit is actually opposite of best fit. So you may think about this process. 10 MB. Let's say this example. 10 MB is available in here. Let's say in here 10 MB is available. Here is also 10 MB is available. Here is 15 MB is available. Here is 20 MB is available. So what it does, like the best fit, in Orr-Speed algorithm is also travels the entire address space. What is a physical your memory address space? Physical address space. Let's say this is from 0, 1, 2, 2, 3. Let's say this is 4,000, kind of like this. This kind of. So it also travels the entire address space, the physical address space, and figure out that the process that is fit for this 8 MB, your new process 8 MB, 8 MB process, best fit for this 8 MB process. So it's figure out, okay, 10 MB, 10 MB, 15 MB, and 20 MB. This is good enough to fit this 8 MB process. And from this whole, and from this backend space, what best Orr-Speed does, it actually choose the space that is actually large one. It chooses always large one, not the smallest one. It chooses the largest one. So for 8 MB process, it will choose the 10 MB whole, 20 MB also, 20 MB whole. That one it will select to fit this process inside this 20 MB hole. 20 MB actually holds 20 MB holes. So here it will make this 8 MB. 8 MB process inserted in this area, and another 12 MB is free. So one thing is that here it also like the best fits. Orr-Speed also needs to traverse entire address space to figure out the all actually available holes that is good enough to fit your 8 MB process or new process. And then from there, it will select the largest hole. So in that case, this kind of problem you just avoid. Make the smaller to create a smallest hole more smaller. This kind of problem you can actually escape by using this Orr-Speed algorithm, but still it needs to traverse the entire address spaces and their entire memory address spaces. This is the 4 different algorithms. Usually, our long-term scheduler can implement to move a process from your hard drive to your memory. In case of memory allocation, is contiguous memory allocation. Okay. Any question?
Yeah, I have a question.
Sure.
Out of this 4, which one would you say is the most used amongst operating systems?
This is very good question. This is our last topic. Next topic, sorry. This is our next topic. So we'll explain. This is very good question. Thank you. We'll explain now.
All right, thank you.
Yeah, really good question. Everybody will tell, oh, which one the best one? Okay. So let's see. If you ask me that which one the best one, in here, in our example, actually, we can we'll see that it depends on 2 things. We can never configure that actually which one the best one. It totally depends on the which order the process is arrived in your memory and where the hole is created. These 2 parameters. We'll see one example now to figure out that which one the best algorithm. So how, before I actually talk about the which one the best, before I talk about which one the best, let's say that how we evaluate the best algorithm for best allocation algorithm. Which parameter, based on which parameter, so that we can actually evaluate that, okay, this is the best, this is the worst one, like this. So if you see that this is your RAM. Also, you know that in our last class we also talk about the degree of multi-programming. So a degree of multi-programming means that you always degree of multi-programming means that number of processes you are able to actually fit inside your memory. Total number of processes at a time you are able to fit inside the memory. This is called the degree of multi-programming. You know that whenever actually computer, whenever you click for a new, open a new process, what CPU does? CPU send a request at first, send a request to the RAM. Is this process is available inside the RAM? Then it is lucky. It will just paste it from this RAM and executes. And if it's not finds inside the RAM, then it will send request to your SDD. And this actual request process actually takes time. It takes if you compare to access from the RAM and compared to the access from the SDD, it's kind of it's very slow process if you paste it from this SDD to RAM and then execute. So we are trying to use as many as process inside the RAM. This is our target, so that whenever a new process created, there will be higher chance to get it from your memory. So also degree of multi-programming also increase. Also your CPU can also execute one process to another process. It has very good flexibility to actually transfer process to transfer actually one process to another process for multitasking. It gets some flexibility. Also, it can use the resource appropriately. So how we evaluate this, which algorithm is best? So we can say our next we will receive some sequence of process next. For example, now my computer is open right now. Within next 10 minutes, computer will receive a sequence of process. Computer will receive a sequence of process. So the algorithm which actually accommodate all of these processes inside the RAM, who is actually able to accommodate all of this process inside the RAM, this algorithm is the best one. We can say this is how actually it's evaluate the which one will be the best. The algorithm actually which can actually fit the maximum number of process inside the RAM. This is the best one. This is how actually we evaluate that which algorithm is the best. Okay. So you know the evaluation criteria, how to evaluate our algorithms, memory allocation algorithm. Let's see one example. We have this is our RAM, and we have here, let's see, this is 100 MB, 100 MB shade. Sorry, already actually taken by one process, and this is 150 MB is backend or hold, and let's say here is another is 500 MB. There is one process in here. Also another is here is 350 MB is backend now, and let's say this is 200. That is one process. 201 process. So in next sequence of process block, let's say this is the sequence of process blocks are waiting to come, are actually waiting to get the space, to taking the space from your memory. What is the size? First one is, let's say 300 MB one, and also another is 25 MB is waiting. This is 125 MB also one, and another is, let's say 50 MB. 50 MB is there. This is 4 process are now inside your SDD. Inside your SDD, they are trying to actually get the space from your memory. Okay, now let's apply our 4 algorithms. Let's see that which actually process can which one actually can do the best thing. Let's say we apply at first we apply the fast fit algorithm. FIR first fit algorithm. Fast fit algorithm. What is fast fit does? It will at first it will now 300 MB comes into the RAM. Try to actually try to allocate inside the RAM, and it will start from this beginning fast fit, and then search in here. This is 150 MB is backend, so it is not good enough to fit the 300 MB. So it keep going on, and then here it's come. Okay, this is 350. So it is 350 is good enough to actually for this process. So it just allocate the memory for 300 MB for this process. Let's this is for allocate the 300 MB allocation, and then here is still we have 50 MB left. This is because it was 350 MB, so 50 MB is still left in here. So next is 25 MB process. Actually try to comes inside the RAM, and what's your fast fit algorithm do? It will again start from the beginning of your memory. Start searching, keep searching, and then it will find in here 150 MB is free space, so 25 is good enough to fit it in here. So fast fit actually, whenever it gets the good amount of space that is fit for your process, it just insert this process in that hole. So it's when the 25 5 MB is process. Here is it's when the 150 MB is available. So it's just insert this 25 MB in this location. So 25 is here. So you have another 125 MB free. 125 is free now. 100 MB free. And next is next 125 process. It comes, and then again fast fit will start from searching in here. This is 125. Okay, available. So it just take this allocation for this 125 in here. Fit it, this 125 MB in here. Next 50 MB process will be in there, and then again it will start keep searching. This is already here is a process. Also here is also one process in here. Here is one process here. There is 50 MB or 50 MB is available in here. So it fit this process in this RAM. So if its memory is if your process comes for a particular time, if your whole is whole size is like this, backend space is like this, and also its process size is in this like this size. So your best fit algorithm is good enough to fit all of these processes. Okay. Any question or comment? This is kind of, we just tested the algorithm for the fast fit algorithm, how it's work. And next is your next algorithm is your next fit algorithm. What's next fit does? What's next fit does? Next fit same thing. Let me again just remove just clear some spaces. So I think it is better to draw a new one. Okay, no, it is fine. Okay, what's next fit does? Let's see. It starts from 300. It comes from 300, so it will start from at the beginning of your actually spaces. Let me change my color for this next fit, and it will start searching from this beginning. There is here it will find 150 MB. not good enough for, it is not good enough for 300 process, and that it keeps going on. Here is 350 MB is available, so it will take the space from this hole. So 300 will be fitted in here as well, the next fit algorithms. So it's left in this location right now. So next 25 process actually comes in here. So instead of searching from this beginning, next fit will search from these places where actually left last time, when it process was actually left at the last time. So it starts from searching in here. So here it's fine. This 25 is good enough to fit this 50 MB. So it takes the 25 from here, and then another 25 is still backend. 25 MB is backend. Backend space. So next 125 process actually comes into the RAM, and then it will search from these spaces. This next week. So it's never search from the beginning. It start from searching in here, where actually it's left the last time. So it starts from searching here. So 25 MB, it is not actually possible to fit this 125 MB process. So and then it's actually goes down. There is also process. You can do this anything. So and then it moves to actually first position, and then again it starts searching from this beginning. So here we can say this is here actually 125. So here it will find this 125, 125 because 150 is available in here. So 125 will take the next piece from here. Also, it has another 25 MB in here, because 125 in here, 25 MB in here. Next, the 50 MB process comes in here. For this next fit, it will start from here. This is 25 MB. So 50 MB is not fit for this 25. Also again search here, also it will find this 25 MB. Can it fit? No, it cannot fit for this, because this is a contiguous memory allocation. If you cannot actually, some part you cannot allocate in here, and some part you cannot allocate it here. Even though there is 50 MB is available, but you cannot do this because it is not in a contiguous location. It is not in a contiguous location. Let's say this is 100, this is 200, 200 address. So it is not a contiguous location. So if you use for this condition, if you use the next fit, so next fit it doesn't work. Next fit doesn't work, and that is good. And then again you apply for another is our best fit. Best fit. Let's say best fit, how it works for this type of process. So 300 comes, and then again it will search the entire spaces, backend spaces. Here is 100. Sorry, 150. It will find the 150 is not good enough to for 300 process. Then it will keep searching. It will find only the 350 holes. Is only one hole that can actually accommodate the 350 MB process. So it takes these places. 350. Let's draw in different color. 350 here it takes also 350, and now we have 50 is available in here. We have 50 is available in here. 50 MB is available here. Let me draw. Okay. Let me draw a new picture. Doesn't look good right now. Let me draw it fast. It was 100 MB. This is 150 backend, and here is, let's say this is 500 MB, and 350 is backend. 50 is backend, and there is some other process. There is no backend issues. Our process sizes. We are working on 300 MB process, and next is 25 MB process, and next is 125 MB, and next is 50 MB. So from this, if we apply the best fit algorithm, how it works, it will what is the best fit said? It just search your entire address spaces and figure out the spaces, holes or backend space that is enough to fit your 300 MB process, 300 MB process, and from these holes, actually it takes the smallest one. Now it will find here, it will find only one hole that is good enough to fit 300 process, and here is no choice. Then it will just insert this process in 300 processes in here. So we have another 50 MB vacation, backend space. Sorry, backend space. And then 25 MB process will be there, and then it will again search the entire. So it will best fit will get the one hole for 150 MB is good, and another is there is 50 MB is left, or the 50 MB is good enough to actually hold this 25 MB process. So from this, it will select the smallest one. Smallest one is 50. So it will insert this 25 MB in here. So 25 MB is left here. And then next is 125 MB process. So again, it will search, and there is only two space, 150 and also 25 is available right now. So from this, only 150 is good enough to fit 125 process. 125 process, 25 process. So here 25 MB is available right now. 25 MB is available. So from here, next is 50 MB process comes inside the DAMs. We have no space for contiguous space for this 50 MB process. 25 MB is here, 25 is here, 25 is here. So you see there is no option to fit it this fourth process. So we can say first fit was work fine. First fit work fine for this sequence, and worst next fit doesn't work. Also best fit doesn't work for this sequence. Let's say how works for the worst fit case. Worst fit case. What is the worst fit does? Okay, let me use the another color for this worst fit algorithm. What when 300 MB process comes for allocation purposes, so it will go through this entire memory spaces and figure out the largest hole that is, and there could be some there could be some more than one hole that is good enough to fit the 300 MB process, but it will take the largest one. So here is only one option. Here is 350 MB is available, is good enough to fit this 300 MB process. So in worst case, worst fit algorithm also takes this 300 MB and also fit it in here. Also 50 MB is now backend. And next is 25 MB process is available. So it will search entire list. So here is 150 is available, and here is 50 MB is available. From this, 150 is the bigger number, so 25 will be in here. 25 will be here. Now, if 25 has gone, so here we have 125 MB is available now. And next is 125 MB process will be here, and then it will also again search. It will find only one space in here for 125 MB. So here is no choice. It will insert this process in here for 125 process, and then 50 MB comes here. So all are already fill up, and then here is 50 MB is available. Only 50 MB it can fit this 50 MB as well. So in worst space is also work well for this sequence of process. Okay, do you get it? Do you have any question? We just for this sequence of process, we just try to implement all of our four algorithms, and from here we can see that best fit and worst fit can actually accommodate all of our processes inside the RAM, but next fit and best fit couldn't do this. So from here, can we decide that first fit and worst fit the best one? The answer is no. Let's see another example. Let's see another example. The clearer drawing. Okay. Let's see another example. The same memory structure. Here is 100 MB. Here is 150 MB. Here is available. Here is 500 is same memory structure, and also, and then 350 space, but it is okay. This is 50 space, but now the process actually arrived some kind of, let's say the process is arrived at sequence of this process like let me show you 300 at first 300 plot by 300 MB plot by 50 MB plot by 125 MB, and also process size, and then 25 MB. 25 MB. Just sequence of this process. We just change the sequence of sequence size of our process. First 300, then 50, then 125, then actually 25 MB process. So how actually first fit algorithm works? When 300 MB is here, it will start searching from the beginning, and then here it will find the 350 MB. Just allocate the memory for this process, and here is 50 MB is there is a hole for this 50 MB. 50 MB you can is a backend space, and then 50 MB comes in here. So it will start from this beginning. Here it will find this 150, and this is good enough for actually for 50 MB process. So 50 MB, here is 100 MB is backend space or unused space is available. 50 is taken by the 50 MB process. Now 125 MB comes in here. So here is 100, here is 50. Even though 150 MB is available, but it is not in a contiguous location, so you cannot do this. You cannot do this. So first fit is failed for this sequence. First fit is failed for this sequence. But how about the next fit? But what actually next fit does? Sorry. What is next fit does? Next fit, what it will start from at first 300 MB. Let's say change my color. Let's say 300 MB will be here. It will start searching and also keep going on. Here it will find the 350 MB hole, and it will fit the 300 in here, process in here, and 50 MB is backend space. Backend space, and then 50 MB will come. So it never start from this beginning. As you know, the next bit will start from in where it's left, and it will find this here 50 MB. So it will fit in 50 MB in here. And then next is 125 MB will be there. So here it will start from here. There is no backend space. Then it will actually comes into the beginning, at the beginning. And then it will start searching. Here it will find the 150 MB. And from here, it will take the 150 MB spaces from here for this process. And then 25 MB process. And again, it will hit it in start from here. Here is 125 is 25 is here available. Here it takes 125 for this process, and 25 available, and it will be fit in here. So now see, now is here is next phase. It's work well for this algorithm. Again, now see the how about the best fit? How best fits work? Our space is 150 and 120, 150 and 350. So for this 300 MB process, best fit will find only one space, which is 350 MB spaces in here. So it will actually insert this 350 MB process in here. So 50 MB will be backend places right now. When 50 MB process will be there, what it will get the 150 MB in here. Two spot it will find 150. Also here is 50 MB because 300 MB already available and 50 MB is 300 MB is already occupied by in this place, and also 50 MB is available. So 50. From this, which one it will take? It will take the smallest one. So it will take the 50 MB one. So it will fit this 50 MB process in here, and then next 125 MB will be comes into the RAM, and then for 120 for fitting the 125 MB process, it will start. It will find only one spaces. It's 150 MB, and then from there it will it is good enough. There is no other option, so it will fit this 150 MB process, 25 MB process in here. So 50 MB is currently backend for this best fit algorithm as well. Best fit. Consider the best fit. Best fit. Now 25, only 25 is what is available. So here it will fit this 25 MB. So best fit is works well for this sequence as well. Now let's see how about the worst fit. Worst fit, we have only two actually backend space, 350. Sorry, let's change my color again. One is 350, another is 150. So when 300 MB comes, there is only one option. One option, only 350. It's actually inserted here for worst fit algorithms. So here you will 50 MB is available, currently available. And then next 50 MB process will be there. And here is two spot it will find. One is 150 MB, another is 50 MB. Two spot is there. So from there, which one worst fit algorithm will choose? It will take the 150 MB because it will choose the largest one. So 150 MB space it will actually choose for fit to fit this 50 MB process. So if it will fit here 50 MB, so if you 50 minus 100 150, so 100 MB is available is backend here 100 MB for the worst fit. Here is 50, here is 150. Now 125 MB process will be there. Here is still 150 spot in here, 150 MB spot in here. So there is no space actually fitted to for this 125 MB process. If you use the worst fit algorithms, even though this is 150 MB backend space is there, but it is not in a contiguous memory allocation. So in this case, we also see that worst fit doesn't work for the sequence of process. So here we can see that whatever you actually saw the last time, we just change this sequence of this process. Then also you can see that also this time also result is also opposite, different. So from here you can decide that actually we cannot decide. We don't know that we cannot decide that who is actually the best algorithm for scheduling a memory. It completely depends on the which order or which sequence or which size of a process comes into the RAM and your backend spaces, backend spots. These two parameters is depends on actually who to fit this to actually to evaluate for evaluate a algorithm who is one actually good or best. But we don't know. We don't come up with any solutions that which one will be the best because we don't know the process sequence or process size. It make also in whole size we don't know. So we cannot actually we can decide that best fit is the best for this allocation or first fit is best for this memory allocation. We cannot decide. We cannot decide this. This is okay. So we are almost end of our class. So if you have any question or any comment to this. Okay. If you don't have any question or comment, we may stop here today. So have a good night. See you next class. Also, if you have any question or comment, you can also ask me or email me anytime. Huh? No worries. Huh? Also, you may find my PowerPoint slide and others in modules.